Yeah, we are recording now. And this is the beginning of a new mini series of meetups of the Clojure community. We are 4 people today, and maybe next time will be more, as we know. And uh, this is a series about the R language for statistical computing. We will explore R. We will be curious about the way the language works and about the ergonomics of our packages and the culture around them, and about the relationship with Clojure. Today, today will be very much about the basics. We'll spend time and ask ourselves questions and explore the little details of the language. And we will begin by introducing ourselves. The friends who are here today are invited to say something, and then we will just start exploring. And yeah, is it okay, George, to ask that you say something about yourself, about how have you been, if you wish, about what you care about nowadays, and so on?
Sure. My name is George. I live and work on the East Coast of the United States, and I work for a financial institution. And I am a hobbyist at best when it comes to Clojure and even data science and AI. And for my day job, uh, I work. We're building a platform internally for this financial institution for data science and AI, specifically focused on data exploration and then serving models and things like that. And so everything currently is done in Python and Scala, and we use platforms and stuff like that. But I've always been enamored with Clojure and its relationships with other languages. So I'm here to learn.
Yeah, that's wonderful. Thank you so much. And by the way, of course, we care about Python and Scala as well. And, maybe one day we should have meetings around those meetings, even though R is maybe kind of closer to Clojure in a way. And um, yeah, um, maybe I'll say about myself. I'm Daniel Slutsky, and I do mostly statistics and probability and math. And I program sometimes in Clojure, but in the past, in different periods of my life, I've been writing in small teams mostly. And John, hello, John. Is it okay to ask that you'd say something?
Sure. Yeah, I'm kind of a closure noob. I dabbled in it a while back, and then I watched Tim Pote do Advent of Code, so I was kind of impressed by the elegance and the mindset. So, in my day job, I don't do too much. It's mostly Oracle and PLSQL, but I've dabbled in R. I think the Tidyverse has been ported to just about everything. I haven't looked at Tidyverse in Julia yet, but I did dabble in R. And my original training was in numerical analysis and mathematics. So I'm kind of interested in Julia, but I'm also kind of interested in the way Clojure approaches things. So that's why I'm here. Thanks.
Wonderful. Thank you so much. Right. So Julia is another thing, and so another thing we're hoping to learn more about. And if you have any thoughts, then maybe one day we can chat about how we could create a series for Clojure people to learn Julia. And yeah, Tim, would you like to say something?
Yeah, Tim, and longtime programmer, some background in databases, just insofar as they've been used as backing stores for applications that I've worked on. But I did a fair amount of writing reports off of that data, and I always liked that part, so I've been gravitating more towards that type of stuff: data analytics, data engineering, maybe even data science someday. And in that vein, I'm learning languages that revolve around that. I have a little bit of experience with Scala already, and a bunch of Python. And then the primary language I spent the most time in is Java. So it was a natural segue for me to look at Clojure. And of all the languages I've looked at, and I've been dabbling in quite a few. I think that Clojure is the one I would pick for just about any general purpose problem. Um, but we're here today to see some R, and I think it'll be interesting to get some perspective because such the language of record for so much statistical analysis that's been done. And this group is, of course, looking to see all the ways in which that can influence the packages in Clojure that can be used for the same sort of thing, and just make sure that we're not missing any tools and understand the insights that have already been had. I'm looking forward to looking at R some more.
Thank you so much. Yeah, and yeah, and of course Java is another topic we should talk about one day. And by the way, Tim was very much involved in preparing this talk. We had a prep session 1 week ago, and Tim, your insights back then 1 week ago were so helpful. So if at any point you would like to drop those insights today, I think it would be very much helpful. And anyway, I think I'll share the screen in a moment and we'll look into a few things. And I think the idea for today is to just wonder about everything and be curious and suspicious about anything we see, and just ask questions and stop ourselves and wonder and explore in surprising directions, so we get a feeling of the language. And also, one thing we may always ask is how it relates to Clojure. What is similar? What is different? Is it equivalent to something we know from Clojure, or isn't it? Right? So we can practice that. And yeah, so yeah. I think you see my screen now, and I'll just move a few things. So you see my screen now. This is the Clojure website. I'm mentioning it because here you can see our different developer and study groups. And I'm mostly talking to the people listening to this recording because a few meetings are coming on very different topics in the different groups, and these are worth looking into. And one special thing we should mention is the Nodge Light conference, and it is all about data analysis, and anybody can propose a talk, and we will help you explore topics, and it is supposed to be very much accessible to lightweight stories, and should be very much welcoming to different kinds of proposals. And it is a great time to talk about it. So if anybody listening to this recording would like to think about proposing a talk, let us talk already now. And yeah, so that is about Clojure. I think the Wikipedia article about R is great and worth looking into, and there is also the main page of the R project of the R language for statistical computing. And so that's one resource worth looking into. There is also the Tidyverse, which is one main collection of R packages, which are very much in kind of harmony with each other and are very popular typically. And that's the main place to look for answers, at least, in the mainstream of the R community, as far as I understand. And there are a few books. The books I've got to know a little bit are for data science. There is the second edition and the first edition. Both of them are interesting. The first edition goes a little more into data modeling with some good stories. So I think you may like to look into that too. And there is advanced R, and you see the authors of these groups are very much central typically to the R community, with Wickham and friends typically. And advanced R is maybe closest to what we are hoping to explore today, because it goes into the little details of the language. And so, for example, you may like these first chapters about names and values and about vectors and so on. And yeah, and there are many other great books in R. So what we will do is program a little bit, and here I have this QMD file, which is a quarter markdown file, which is one way to write some markdown notes and have some code, some R code inside, so we can insert those R blocks where we compute something, and we can when I have an R block, I can evaluate with here I use Emacs, but other editors also have great support. And so now when I evaluate, it asks me to open the R terminal and now, or R console, or REPL as we like to call it, and now we can compute. So we can do some arithmetic and see things computed. Oh, sorry. Oh, what did I do? So right, so we can compute. So that is our experience, and we'll also visualize some stuff a little later. And let us, anytime stop and wonder about what we see. And of course, this quarter markdown file is part of the quarter project. That is just a nice way to create notebooks in R, but you can also have just a plain .r file and explore from there, and the experience will be similar. Somebody was looking to say something, maybe. Oh, no? Yeah.
No, I was asking, you were evaluating it from the Quarto notebook or from the REPL, R REPL? I wasn't clear at first.
Oh, yeah, thank you. So yeah, I'm evaluating from the notebook. So here I have a key binding in my editor, and when I send the code to the console, it is just being sent to the console, but I can stay editing the Quarto markdown file.
Perfect, thanks.
Right? Yeah, thank you. And yeah, and you see Quarto has some great integration with different editors. So you can read here about how you integrate it with your favorite editor or IDE, and here Emacs is just one of them. And right, and maybe let us do another thing in another code block. So we can load a package, and one favorite package is the Tidyverse, which is just a collection of a few R packages, or libraries as we call them. And so when I load this for the first time, so I send this to the console, you see it loads this list of famous libraries for different kinds of needs for data analysis in R. And maybe let us load another one, which is HTTPGD. That will be used for data visualization, for interacting with a browser view for our data visualizations. So I load that too. So yeah. And now let us set up data visualization. So HTTPGD is kind of handy for that. And sorry, it is just a bit about the setup, but I think in most editors that will be handy. So you can call this HGD function. And what it does is, you see, it starts a web server that will be serving data visualizations to the browser. And then you can say like HGD browse, and then it should open a browser tab, which is empty at the moment, but it will be a handy way to view our data visualizations. And let us visualize something. And you see, I'm mostly just kind of trying to get things going, and then we'll dive more into the little details of the language. So let us write something. So let us create some random numbers. We can create random numbers with the many functions that begin with the letter R for random. So for example, there is the rnorm function that can create random normal numbers. And so these are, if I run this, you see I get many numbers. And these are numbers which are sampled from the so-called normal distribution or standard normal distribution that is known for the bell shape it has. So we can talk more about this later, but if we can, visualize this, so we can sample these by random, and then we can create a plot for them. So one way to create a plot is by passing them as a data frame to the ggplot data visualization library. I think we'll focus on this because it is the famous one and is so inspiring in many ways. So we can do something like a ggplot of a data set that has, here I'm creating something called a data frame, which is basically a table structure that has R norm as a column called X. And we will define the aesthetics to be X equals X, and we'll add a histogram or a density maybe. So please don't worry for a moment about all these details. We can make all of them clear later. And when I call this, you see it is sent to the browser. And that's thanks to this HTTPG library that is making things comfortable for data visualization. So I just wanted to kind of make sure that we get things right, and so we can, have things visualized. And otherwise, they would be sent to a separate window in your operating system, and you might have some styling problems. And, I think this way with the browser is maybe more consistent in a way. So any comments so far, any questions or thoughts about what we're seeing? Great. So I think what we'll do now is also demonstrate another feature of this quarter document we're using. And that is that we can visualize the whole document. So here I have in my editor, I have this quarter preview command that sends the whole document to be visualized. And you see, oh, didn't work. Oh, something is not, because I didn't save. So now I saved the document, and I will ask to preview again, and it updates the view. So that's another way to use quarter, and and here it is updated with the many random numbers. That is kind of stupid. Maybe I'll remove this from the notebook, and I save again, and I send it again to the preview, and it should refresh again. And this other browser tab is complaining, but never mind about it. So now we have our notebook as a whole story of our progress, right? And we can have, typically markdown and so on. And so that's the experience with Quarto, which is kind of recommended. And we also care about it because we like Quarto in our Clojure notebook making. And so we can update this view. And so now we'll have these markdown headings and so on. Great. So what I'm proposing is that we will have a little exploration of a data set just to get a feeling of the experience, and then we'll look into the language if it makes sense. And so we have 1 hour till the official end of this meeting, and some people may then look to stay longer. And so one source of data sets for data analysis exploration is the Tidy Tuesdays project of the R community. And this is a habit they have to explore data in Tuesdays. And you see, they have been sharing all those many data sets and data explorations throughout the years. And we look into one of them and just explore a little bit, just so that we get a little bit of the experience. So I think, yeah, maybe the Shakespeare one is nice. Oh, is it? Oh.
That's pretty cool that they have a site where they do that exploration every Tuesday.
Oh yeah, right. Yeah, it is. Yeah. Why don't we do that? Right. Right. So Shakespeare. I remember this Shakespeare data set that used to be useful. Right. So we have the Shakespeare dialogue dataset, and you see there are clear instructions of how we can load that. So let us load the dataset for Macbeth, and you see this this is how we call a function read CSV from the namespace readr, which is associated with the package readr. And this is supposed to be available now because it is part of the Tidyverse collection that we already have. And so when I call this, it should, yeah, maybe I should open the R console again here below. So yeah, it did load the dataset, you see, with some warnings, and that look okay. So now we can, look into Macbeth. Let us see what we have there, right? So we see that it is a table of the table type, which is one of the nice table types in R. And table is this, way of wrapping tables with certain user ergonomics. And we see we have the different characters and the little pieces of dialogue they practice in the play Macbeth, and just everything that goes on throughout the whole play. So we can count, for example, how often each of them speaks, right? So let us do that. Oh, sorry. So here we will process Macbeth with the pipe operator. This is very similar to what we have as the threading macro in Clojure. It just passes whatever we have as the first argument to the next function call. Sorry for this. So we will call a function that will take these data and group by the character, right? So we can group by character. And then when we do that, we get a grouped data set. And you see now it looks the same, but it says we have 42 groups. So now we can summarize our groups. And one way of summarizing is by adding certain columns which are aggregating over the groups. So one way is to call this function. Maybe let us not explain exactly what is going here at the moment. This will count the number of rows per group. So when we do this, we get a count. Count is just the column name we created by counting the number of rows per group. So we have, the different characters of Macbeth and the times where they spoke in the play. And we just continue a little more just to get the feeling of this pipeline approach that may be familiar to Clojure people, maybe similar and different from what we do in libraries like tablecloth in Clojure, right? So now maybe let us order this by the count, right? So Is it like that? Oh no. Oh. Oh, is it arrange? Arrange. Right. Sorry. So now it is maybe not the most useful order. I would like it the different orders, and I don't remember how. So I can write question mark arrange and ask for help. And when I do this, I should get some help about the arrange function. And can we order it the other way? So, oh, so we just wrap our call with desk for the descending. So, right, so you see, calling for help is very common here in R, and that's something we very often do. So now I'll just ask for like descending by column. Let's look for the terminal again. So when I do this, now we see the character Macbeth is the most frequent one in the play, which makes sense, right? Is it surprising for those who know Macbeth? Does it make sense, right? I think, yeah.
So I have a question. The
Yeah.
Tibble, we didn't have to specify or convert the Tibble data type into something like a different type. It just R just understood. It's a table. It's a table. So like in Python, if you use pandas, you have a data frame, and you have to do some converting back between arrays, data frames, all that kind of stuff. We didn't have to do that. It's just a Tibble is the data type.
Yeah. So yeah, thank you for this. Right. So there is something called data frame. Is a table data type of the core R language, and there is something called tibble, which is another type, basically wrapping data frame, added by the tibble package. Right. So the usual way in R to work with tables is the notion of a data frame that we saw earlier for a moment. It is part of the base language, right? It is like the base language, and it's a very basic notion that is not a complicated data structure. Tibble is actually very similar, but it's just wrapping it with slightly different behaviors, like the way it is printed and the way it the way certain functions will act on it, which is considered a bit safer and more consistent than the base language. So it doesn't add much to the base language. Does it make sense?
It does. Thank you.
Yeah, thank you. Right, so in a way, it is a more basic notion, more foundational notion in R compared to Python, where it was added by pandas. Yeah, thanks. So yeah, that was very helpful. So now we get to this table or table where we got these counts, and let us just visualize it for a moment, and then we look more into the little details of the language. So yeah, let us keep going with this. And now we can pass this to as the data for ggplot, this famous plotting library. And here again, we define the aesthetics, and we'll say that our y-axis maybe our x-axis would be the count, and our y-axis will be the character. And when we create this, we create a plot, but we need to add to the plot some geometry, and we add geom point, for example. So it will be a point chart. And when we send this to be visualized, it should be sent to the browser. So I recall that we had to HGD browse so that we'll have the browser view for plotting. And now we have this plot with the browser view, but there are so many details here. So maybe let us first filter the data. So we can filter by maybe count being at least 20 or 20 times they said something during the play. So it will be less crowded in the plot. Right? And maybe let us make the size of the points bigger. And maybe let us also order this so that you can, instead of saying count, you can reorder count by character. And later we may, maybe today or another time, we may understand what these things are actually doing. But this should, oh, that didn't work. All right, because I actually want to reorder character by count. Right. Right. So yeah, Macbeth is the most frequent one and so on. Yeah, so this kind of might feel like magic, and let us keep it this way for a moment, just to wonder about these things, because we haven't spoken about the more basic stuff of the language. So that's a little intro to the experience, and this is the Emacs editor, but you will have great experience in Vim and VS Code, and of course the RStudio editor, and now there is something called Positron and so on, other editors and IDEs for R development, and Jupyter notebooks and so on. Right, so yeah, so that's what we have so far. Any thoughts about this? Any comments? What is most strange and surprising so far?
I think for me, I've watched what your team is doing for Node, right? For Clojure. The idea that all these libraries are built into Tidyverse is pretty amazing. Because if I were to do this in Python, I'd have to import like 5 different import statements to get the plotting feature, the data frame feature. So that's pretty cool. And then obviously the piping is awesome.
Oh yeah. This comment helps, I think. Yeah, to appreciate what we're saying. Right. We didn't need much setup for all this to work. Right. Yeah. Great. Yeah. So now let's talk about the language. And so we did see a few things with numbers. Let us look into this, because these are kind of the primitive data types. And so we did see things like rnorm, like for random normal numbers. And right, so this is rnorm. Yeah, let's have less of them. And also we can create a sequence of numbers. That's another thing. And we can create, yeah, maybe we can repeat a number many times and so on. Right? So, and we can concatenate. We can concatenate like a sequence of 10 numbers with 10 random numbers. Right? What do we see at the bottom actually? What is that? It is just the numbers. And on the left, we have, this like index saying 11 here. What does 11 mean? It means this is element number 11 in our sequence, in our vector, right? So it is just a way to kind of get some orientation with our vector of numbers. So these are all called atomic vectors. They are atomic because it is a very basic data type. It cannot be split into more basic data types. That's the most primitive thing we have. So you can have atomic vectors of numbers. You can also have atomic vectors of Booleans, like you can repeat true 5 times and repeat false 5 times. Oh, sorry. 5 times and concatenate these, right? So that's another thing you can do. So these things have types. So we can ask for like the type of this thing, for example, and it will say logical. And if we ask for the type of this thing, it will say double, like double the double floating point number and so on. And so we see that these things have these primitive data types like logical, which means Boolean, right? Right? So, and we have a few other, yeah, sorry.
Should a type be a sequence of some sort? I know that it's telling me the sequence is of type logical and double.
Yes, that's great. Right, that's a moment of surprise. Thank you so much. Right, that's kind of the point. There is nothing more basic than this. Everything is an atomic vector.
Ah,
So, yeah, that's kind of a moment of surprise. So if we have something like just the number 14, this has the same type. And it is of the same type. It is an atomic vector as well. There is no difference between 14 and the sequence, and a sequence of things, right? So, these, like the sequence between 13 to 14 and this, they are the same. They are both, oh, sorry, this is integer actually. So yeah, that's not a good example. So maybe like, no, 3. This is double, this is double, just the same, right? Type of a sequence of integers will be integer, and type of 14L, that's a way to say you want an integer, right? So they are all atomic vectors. And you can ask for the length, and the length will be different, right? So the length of 13 to 14 will be 2, right? And the length of 14 alone will be 1. It is just a length 1 vector. Does it make sense? Or
it makes sense.
yeah, strange, of course, isn't it? Right? But the language doesn't have anything simpler than that. And right, if we, yeah, and in a moment we could think about other languages like Clojure and the equivalent. So, but yeah, that's the most basic thing. And if we want to create a vector of a few of them, then we can just concatenate, right? So we can create something like that. So here we just concatenate 4 different vectors into one, right?
So is that 4 different vectors, and the output is a 5th vector of all them concatenated?
Yes, it does allocate new memory.
Gotcha.
Yeah, a new vector, copying and concatenating all the 4 of them, right? So yeah.
When you say atomic, that normally to me means that I'm going to always create new memory, or can I overwrite something within that memory space? So if I had a variable assigned to one of these,
Yeah, right. Let us change something, right? So we can like define an R object. That's a new thing, right? Here we define an R object, and which is like a var in Clojure if you care about it. So this will be maybe this thing. And here we look into printing X, so that's X. And here we can ask to change X in a certain position. So X at position 2 will be 1000. And then we look into X again, right? So it did change in position 2, which is the second position, not the third, right? So yeah, we can mutate, and this is overriding in place, right? It is overwriting in place. Sorry, yeah. So is it?
yeah, well, that's overriding the elements of X, but can you say X now equals something different? Does it know
Oh
like
yeah, yeah. X equals like a few random numbers, and then X will be a few random numbers, and probably the old memory was garbage collected by now.
okay.
I think, or maybe we should call like garbage collection GC, some system GC, something like that. I don't remember how. Oh, I'm confusing with Java. Sorry, I should remove this. I forgot how to garbage collect. But yeah, but it is just, in a way very similar to what might happen in Java with Java arrays. So these are kind of
Okay.
similar arrays in certain languages. And the idea is that these atomic vectors, because you know the type of the elements, they are contiguous in memory, right? So right, so like arrays in C and Java and so on, right? So they are supposed to be relatively efficient. And maybe let us move to another data type in a moment, but first let us maybe see a few other things. So another thing is that we may define an R object to be few numbers. Maybe let's take these. And then Y, another R object, can be assigned to whatever we have in X. And here it didn't copy. In a way, it just is a reference to the same value. Right? Makes sense. We have two references, and Tim last meeting, where we in the prep meeting, Tim taught me I should call these references, and right as is maybe the proper term, right? So, right. So this could be a huge data structure, and we just have two references. And now, what happens if we change Y at some position? Then we copy on modify. So now at this point, the whole structure of 6 elements will be copied to another copy so that X and Y can remain different. So, right, when we do this, X remains as it was. So I should go step by step. So X will remain as it was and Y is changed. Does it make sense?
It does.
Yeah.
Sounds expensive operation.
Yeah, and yeah, so it takes care to keep the structure contiguous in memory, an array of primitive type, which is efficient in certain uses, but we should just know when these things have to be copied, which can take some time and space. right? Yeah, so that's one way of semantics. And in Clojure, we have some things which are similar and different to these. And yeah, the alternative would be to use a more complicated data structure, like what we have in Clojure, those persistent data structures that try to share memory between them, but they're not as lightweight as just an array of numbers. They are more heavyweight and they are not contiguous in memory, so they will be less efficient in computation. So it is a trade-off, and copy on modify is one of the simple practices that try to make things, reliable and unsurprising. So at least that's what's happening here. Yeah. Any comments about this? Anything we should explore before we move to another data type? Yeah, and I really like your comments are so helpful. Yeah, exactly. The kind of things we should have in this session, I think. And yeah, so let us move to another thing, which is lists. And so lists are different. Lists can have anything inside of different types. Oh, maybe before we do that, let us talk about a little more about vectors, about atomic vectors, sorry. And let us see what happens when we concatenate different things of different types. So we can concatenate a vector of numbers with a vector of booleans. What happens is that the booleans are turned into numbers. So it does whatever it has to, if it can, to keep everything of the same type, so it can remain an atomic vector of one type, right? And so there is some type coercion here. And if we have maybe strings here, or character values as they are called, then everything is converted to strings. So there is some hierarchy where logical true or false is converted to numbers, and numbers are converted to strings. And things are kept all the same type so that it can be contiguous in memory. About the strings, a string in R has only one instance. So these two ABC are the same value. They are pointers to some space where the whole sequence A, B, C is kept. So this array is basically an array of references to that lookup table where all the different strings have each one copy. So that's a special case of an atomic vector. And so these are all atomic, right? So this is what they call type coercion. And lists are different. Lists can have things of different types. And so on, right? And other lists inside. And lists are also printed differently. That's the way a list is printed, with these additional brackets, and you see this way we see the nested structure. And here, at least in this default behavior, the way things are printed, we see that printing in R tries to be friendly in a way to kind of show us the structure we have, but it doesn't show us the code that would generate the structure. And in Clojure, of course, or in typical Lisps, the two are the same. in Clojure, when you print something, you actually print the code that would allow you to create that structure, right? And here, in a way, we are breaking the real read eval print loop, because we are printing something that cannot be read as code later. But it is quite handy to see the structures this way when you get used to it. So these are lists. And what happens when we concatenate lists? So we can maybe write this list as concatenation of two different ones. So this is one of them, and this is the other, and we can just, oh, sorry. And we can just concatenate that. So this is the same structure, and you see concatenation of lists is a list, while concatenation of atomic vectors is a vector. So here, the logic is different. We no longer make sure to make everything of the same type, and we no longer make sure to have everything contiguous in memory, because we can't with all those varying types. And yeah, and basically lists are represented internally as pointers to the different values they have inside. And in the advanced R book, you can have some nice description of this. I think it is the names and values chapter, maybe, where you have those diagrams where you see, for example, that an atomic vector, oh, sorry, is contiguous in memory. But a list, or where do we have a list? Oh, maybe in another chapter. Oh, yeah, right. Sorry. So I should kind of scroll through. I think this chapter of names and values in the beginning is very, very much recommended as a way of getting a hold of what is happening in terms of memory usage and so on. So these are atomic vectors, which are contiguous in memory. And this is a list where all elements are basically, implementation wise, are pointers to where the values are held. And then there are other structures we may talk more about. So yeah, I think these diagrams are very helpful to get a sense of what is happening. So any comments about lists and so on? Maybe we should also kind of show that lists can have like longer vectors inside, right? So it can be more elaborate. And then when you print it, you'll see the longer structures inside. Yeah. So, right. And then the idea is that almost everything can be represented by these types. And if you're a Clojure person, then you're not surprised, because in Clojure, we really like representing things in plain data structures like vectors and maps in Clojure. And these are not the equivalents of Clojure vectors and maps, but are kind of similar. Maybe another thing we should say is that lists can be named. And actually, atomic vectors can be named as well. So let us maybe have it as a separate section here. So you can create an atomic vector like x1, 2, z3. Can I do that? Oh, sorry, I should put it in a code block. So that's one way to name the vector. Now you see it is printed this way with the names. And you can also name a list. So we can also have a list of these things named other things. And then it is printed this way with the X, Y, and Z. So this may feel like a Python dictionary now or a Clojure map, but it isn't exactly, because there is no hash map behind the scenes to make this efficient for lookup. So we may, do something like putting something in a list like this, and asking for elements. That's how you refer to an element of a list, with a double brackets, element named y. So this will give you 2 because this is y. But you can also have like, you can also write something like $y. That's another way of writing it. So it does work, but this is inefficient for big lists, since there is no hash table behind it. So it is not exactly like a Clojure map that is supposed to offer efficient lookup, right? But it does represent a named structure, so you can create those JSON-like structures with names, with lists. And so basically you could represent so much this way. And maybe another thing we should talk about is that you can have something called attributes, which are like metadata in Clojure. And this will allow you to create a type system on top of that and many more things. And then basically you have everything you need to create a whole language with everything of everything. And not all of R and its packages are implemented this way, but a lot of it is implemented just from atomic vectors, lists with names or without names, and attributes, which are metadata. That does allow you to represent so much. And yeah, so any comments so far about this? We haven't even spoken about functions and all that, and we may in a moment, but maybe it is a lot already to think about. Maybe I'll just say that there is another thing called environments, and they do have hash tables behind them. Unlike, yeah, they are like named lists with hash tables behind them. So lookup is efficient. And they are used mostly for scoping. You know, where in a certain context, like inside a function call or in a nested function call, certain variables have a certain value determined by the scope of where you are in the code. And the way scope is implemented is by a certain hierarchy of these environment structures. And there is a beautiful chapter about it in this book. And we will not go into that so much today. But I think that's one of the really interesting parts of the language, that the whole story for scope, the way things work in function calls, and the way you can kind of break the assumption, the usual assumptions of function scoping, all of that can be described with basic data structures and relationships. Maybe this is kind of maybe similar to the hierarchy of Java class loaders that you have in Java, but in a way much simpler. And so maybe that's something we could learn one day. And yeah, does anybody have any thought, any comments? So let us look into functions for a moment. So let us maybe, for example, look for the mean function or median function. Right, the median is in a way the middle value in a set of values. Oh, sorry. So median, And oh yeah, actually, let us talk about missing values first. That would be good. So you can have missing values, and the whole of the language is built to respect this notion of missing values, which is kind of central to statistics, and we will see that why this matters in a moment. But this is one valid value you can have in your data structures. So now let's talk about functions. Sorry. So let's look into the median function. Oh, yeah, maybe let's first a more basic one. So you can look into the absolute value function. You can apply it to an atomic vector of numbers. And you see the absolute value. What it does is to remove the sign, the minus sign from everything, right? That is what it does. And you see that functions typically respect atomic vectors, many functions. They take atomic vectors and return atomic vectors of the same size. This is typical to many of the functions, and you can kind of this way work efficiently in contiguous spaces in memory, you know, this so-called array programming or vectorized programming that is handy in making computation efficient. And then they often respect missing values. So we can do something like add a missing value to this atomic vector, and the absolute function would just keep it missing. Right? Makes sense, right? So this is handy. This way you kind of propagate the missingness along your computation. And then they can also have named arguments. So if we look into the median function, so the median function, you know, if will return the middle value of a sequence. So if we have like a sequence of maybe 3, 4, 9, 10, 2, and 15, then the middle value is 4, right? Because half of, or roughly half of the values are below and roughly half of them are above 4, right? So the median of these will be 4. 9, sorry, why did I say 4? 9, right? 9 is the middle value, right? So that's median. But what happens if we have missing values with the median? Like what if this 4 is missing? Then the answer is missing. I cannot compute the median, but we can add another argument that will say, and let's look it up, NARM, right? So should we remove should we remove missing values? And if we make this true, then it can compute the median. And then, you know, it will take the middle value between 9 and 10 because they are the candidate of being the middle ones, because there is an even number of non-missing values in this case, right? So we can have named arguments, which are additional arguments that can be referred to by name. Here, the name of the argument is NARM, and you see a point, a period is a valid character for variable names and argument names and so on. So does it make sense what we're seeing now? Is it surprising again? Does it raise any questions?
Makes sense.
Yeah, thanks. Right. So functions can also see the expression calling them. So let us see an example. So you have the special function, which is, not special in any way in terms of the R language, called with, that will take a list of values, x equals 9, y equals 11, and compute an expression like x plus y. This is returning 20. So what is happening here, right? What is actually happening? So you see x and y are not bound to any value out of this function call. Oh, actually they are, because we did compute that earlier. X was this thing and y was this thing, right? So x and y did have other meanings out of the with call. But when we call with, x and y will be bound to these values of the list structure we're passing. So with overrides the scope, overrides the environment in which x plus y is evaluated. And if you think about it, then to do this, it cannot take the value of x and y, because the value of x and y doesn't mean what it has to mean before calling the function. And so the expression x and y will only be evaluated inside the body of the function with a different scope that the function creates. So this means that the function needs to see the expression x plus y, right? So the above function call handles x plus y as an expression and evaluates it in a modified scope environment. So a Clojure function cannot do this thing. A Clojure function cannot see the expression you're passing to it. If you wish to do that, you'll need a Clojure macro. But in R, all functions can see the expression calling them. So they can do these kind of things. And we actually saw these things happening in our calls earlier to here, for example, when we were processing tables and we were arranging by count, count didn't mean anything outside of this context of calling a range. Count is a column name in the table we're processing, and a range modifies the scope so that this expression would mean something, and so on. So that's something which is kind of central to the ergonomics in the R language. As we know, in Clojure, we often avoid macros because there is much risk in this surprising behavior that breaks the usual semantics of the language. And so in Clojure, many people would avoid macros as much as they can. In R, they wouldn't avoid macros, but they would try to be kind of civilized about using them. And you see the metaprogramming part of the advanced R book that talks about all that. And and you know, they are trying to offer in that metaprogramming chapter a certain way to use these powerful properties of the language, but you know, which are called sometimes non-standard evaluation, right? But do that in a way that will be unsurprising. So they call it tidy evaluation. The tidy word is used in many senses in the R community. Sometimes like what Clojure people, the way Clojure people use simple, right? So in the R community, they like the word tidy, and here tidy evaluation means making non-standard evaluation unsurprising because we implement it in certain unsurprising ways, which are kind of agreed upon in the current culture. So that's part of the powerful stuff in the language, and we can explore it further. Yeah, so we have 10 more minutes till the official time. Maybe we wish to think about where we're going, what else we may wish to do. And yeah, we could look into more data types like data frames and so on. Yeah, let us maybe just briefly look into data frames. So right, we can create something like, maybe let us call it df as a data frame of some values. Let's print it, right? So it is this table-like structure. And what is it actually? So we can ask for the type of it, and it says, oh, type of list. But then there is more detailed type information called class, or sorry, sometimes more and sometimes less detailed called class that adds that it has the data frame class. This is part of the polymorphism that, sorry, it is part of one form of polymorphism that the R language has, where you can assign certain classes to values that will determine the way functions are applied to them. So in a way, a data frame is a list, but with additional information attached. And I think we can look into the attributes. So attributes is a list, you see, that's the metadata of a data frame. And it has the names of the columns, the class, which is data frame, and the names of the rows. So all of these parts of the information are data structures which are added to the actual data structure as metadata. And this metadata will determine the way things behave. So when we, so basically a data frame is a list of columns, but with some additional decorations, right? So you can, for example, print a data set, right? So what happens when you print it is determined by, you know, the print function. And if we look up the print function, oh, we didn't say, but we can write the name of the function and print a function and see the actual code of the function. But the code of the print function has this dispatch on type. That is what it means when we see use method in the code of the function. Use method means that the function print is a generic function, as they call it in R, similar to maybe a multi-method, as you call it in Clojure. And so print will have different versions, like print data frame. And when you pass a data frame to print, it will actually call print data frame, since data frame was the class of that value. And then the code for print data frame is actually quite detailed. In this way, we get this nice way that when we print the f, right? So when we print the f, use actually print data frame. And so the F is printed this way, which is kind of specialized to the class data frame. So you see, there is nothing sophisticated about the data frame type. It is just a list of columns, which can be relatively efficient for certain use cases. Sometimes it depends on the way you implement functions with that, and we'll talk about it some other time maybe. So these are data frames, which are kind of central to the story. And yeah, we have a few more minutes. Maybe we should think about what should happen next. Maybe I should stop recording for a moment. So stop sharing, sorry, so we can discuss things. Yeah, so that was a little intro to the R language from a Clojure perspective, and we'll keep doing that. We look into R packages and into the relationships, different ways to call R from Clojure, maybe some ways to call Clojure for R, which is maybe less common, and similarities and differences between the languages and so on. And yeah, if anybody has any thoughts about what should happen in the coming meetings, then it will be great to chat anytime and think about it. And if there are any ideas now, any things we should explore further, then we can keep going with this call. And otherwise, I'll stop the recording and we can keep chatting about anything for those who wish to stay longer. Yeah, maybe, yeah. Right. Yeah, so if there is anything much more to explore, then maybe it is a good time to stop the recording, because the time after the recording is always so great to chat about other things. So we're saying goodbye to our listeners and see you on the next time.